Welcome back to the wonderful world of astronomy. This is Chapter 5, Light and Matter. In the first two videos of Chapter 5, we've been looking mostly at light, and now we're going to get more into focusing on matter. So this is Part 4 on atoms. So what is the structure of matter? Matter is made up of very tiny particles called atoms. And as you can see here, it says 10 million atoms roughly could fit end to end across this dot. So they're very, very tiny. Now, if we zoom in on this, pretending, okay, so 10 million atoms across this dot, we zoom in and we're going to look at an atom. And an atom is composed of a nucleus at the center. It says the nucleus is nearly 100,000 times smaller than the atom, but contains nearly all of its mass. So if this big cloud right here is the atom, 1/100,000th of its size is the nucleus right there containing most of the mass. And when we're in the classroom at the college, the scale I use is imagine that an atom is the entire size of our classroom. The nucleus would be a grain of sand sitting in the center of the classroom, and all the rest is empty space. Now there's the nucleus, and let's go over here, zooming in. The nucleus is composed of two types of particles. They are protons, and the illustrator uses red spheres for that, and neutrons using gray spheres right there. They don't actually have color as such, but that's what the illustrator here has done. So these two charges, protons and neutrons. Later, we're going to talk about the electrical charges of atoms, the electrical charge of different particles. And for now, you should know that a proton has a positive charge, and a neutron is neutral, so it has zero charge. And then spread out, it says smeared out around the edge of the atom is the electrons, and the electrons have negative charge. So we've got the nucleus at the center with the protons and neutrons, and then the electrons that are whizzing around very fast. And in this animation, you see the small dense nucleus that contains protons and neutrons, and the electrons surround the nucleus. So three particles that are in an atom. Three types of particles, rather. Now, when we describe an atom, there are two quantities that we use. And the first is the atomic number. And the atomic number is the number of protons in the atom. That's what's going to define what element it is. So for example, hydrogen is known as element number 1, and it's known as element number 1 because it has one proton. So its atomic number is 1 because it has one proton. Now the other quantity we use to describe an atom is its atomic mass number, and that is the total mass of the nucleus. It's the number of protons plus the number of neutrons. So for example, here we have the most basic atom. It's hydrogen. It's just simply got one proton in there, 0 neutrons. So it's got an atomic number of 1, and it's got an atomic mass number of 1. Now also, it has electrons. In this case, it has 1 electron, but we don't count that when we're talking about the atomic mass number or the atomic number. It doesn't count towards the mass because electrons, while they do have some mass, it's so small we usually don't even count it. Now you can see this notation right here. The name hydrogen is spelled out, but we can also write it as its symbol H. And that 1 that's to the upper left hand means it's its atomic mass number. So that's known as hydrogen 1. Let's look at another example. This is helium-4. Now helium is known as element number 2 because that's its atomic number 2, because it has 2 protons. Now you can see the picture here. The 2 red spheres represent the protons. The 2 gray spheres represent the neutrons. So helium, by definition, always has atomic number 2 because of its 2 protons. The number of neutrons can vary. In this particular case, it has 2 neutrons, as you can see in the picture. So 2 protons plus 2 neutrons gives an atomic mass number of 4. And so the notation we use, we can call it helium-4. By the way, it also has 2 electrons. usually, not always, but usually the number of electrons is the same as the number of protons, and I'll talk about that later. Let's look at another example. Carbon, by definition, carbon is any atom that has 6 protons in it. So carbon's atomic number is 6. In this case, it's got 6 neutrons as well. It doesn't have to have 6 neutrons. Carbon always has 6 protons, and it can have a varying number of neutrons. But in this case, it has 6 neutrons. So 6 plus 6 gives an atomic mass number of 12. And it also has 6 electrons, matching the number of protons. So I want you to remember that the atomic mass number, it's basically the mass of the atom, is the number of protons plus the neutrons. We don't count electrons because an electron is actually about 1/1840th the mass of a proton. So it's very, very tiny, very low mass. So we essentially don't count its mass. We just count the protons and neutrons to get the mass number. The atomic number is simply the number of protons. So let's look at this. Let's quiz ourselves here. How many protons and how many neutrons are in this atom? So this is lithium. Its symbol is Li. And now I'm adding something new here. I haven't shown you this before. If there's a number in the lower left hand of the symbol, that is the atomic number. Now, oftentimes we don't have to write that. It's a bit redundant because the chemical symbol lithium, and if you have a periodic table, you can see that lithium is element number 3. So if it's lithium with the symbol Li, there will always be a 3 here, or there should always be a 3 that belongs there. So sometimes we write it, sometimes we don't. But so that atomic number being 3, that means it has 3 protons. And then you look at the 5, and we want to know how many neutrons. Well, remember, it's the protons plus the neutrons that gives the atomic mass number. So we're going to take this 5, subtract the 3, and that tells us that there are 2 neutrons. So 3 protons plus 2 neutrons gives us the total of 5. And there's a picture of it there, lithium 5. Let's do another example. Now, by the way, you see that 4 down there and to the left. It's written in red. It doesn't always have to be written in red. That's just the way the graphic that I found has it written. We're looking at the element beryllium. And the question is, how many protons and how many neutrons? So we're going to look at the lower left hand. That's the atomic number. And it's 4. So that tells us how many protons there are. So 4 protons. So if the atomic mass number is 9, how many neutrons does that leave us with? And you should get 5 neutrons because 4 plus the 5 is going to give 9. So we're looking at what's an isotope called beryllium-9. Here's a periodic table of the elements. And they start with element number 1, which is hydrogen, element number 2, which is helium, and then we go back to the left. Element 3 is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And I know it's too small to see on the screen and the resolution isn't that good, but each of these in the upper left hand is a number. So number 1, number 2, number 3, number 4, and that is the atomic number. So every element is defined by its atomic number. Hydrogen is always 1. Helium is always 2. Lithium is always 3, etc. What can change is the mass, and that has to do with how many neutrons you add or take away from it. You can see how many elements there are. On this table, they go up down here to the lower right, 118 elements. In this class, we will mostly be focusing on maybe the first 20 elements or so. So there are many elements we're not going to talk about, or maybe I'll occasionally mention them throughout class as it's necessary, but the top 20 are the ones we'll be focusing on. You don't have to memorize them, except you should know hydrogen number 1 and helium number 2, because those are the most dominant elements in the universe. So most common elements in the universe, hydrogen number 1, helium number 2. Now you can think of those numbers there as the rankings, meaning hydrogen is the number 1 most common. Helium is the number 2 most common, but also those are their atomic numbers. Hydrogen is element number 1, helium is element number 2. Astronomers sometimes refer to all other elements as heavy elements or metals. Astronomers sometimes refer to all other elements as heavy elements or metals, and non-astronomers think this is crazy. It is a little weird because if you take a chemistry class or just in everyday life, you think of metals as that's a term that's reserved for certain elements like gold and copper and iron and nickel that have certain properties. But in astronomical literature, often every element that is lithium or higher, so number 3 or higher, sometimes they're referred to as metals. The next term I want to teach you is an isotope. Now, two isotopes of an element, they have the same number of protons, but different number of neutrons. So they're in the same family, they're in the same element, but they will have different masses. For example, you can see in the picture 3 different isotopes of carbon. Carbon has more isotopes, but here are 3 that are shown. So they're called carbon-12, carbon-13, and carbon-14. Carbon, by definition, has 6 protons. It's element number 6, that's its atomic number. But there can be different numbers of neutrons. So on the left, you have 6 protons plus 6 neutrons. That makes a mass of 12, and it's called carbon-12. Notice the different ways that it can be written. Carbon with the word written out and then a hyphen, then 12, or the element symbol C with a 12 to the upper left hand. And if you're writing it out like that with the symbol notation, don't just put the 12 in any random place. It specifically goes in the upper left hand because the other places, like the lower left hand, the upper right hand, etc., they're reserved for other things. You've already seen how the lower left hand can have the atomic number. So there could be, right where my marker is, there could be a 6 right there. The other isotope is carbon-13. So this means 6 protons plus 7 neutrons. And then a heavier isotope of carbon is carbon-14. So 6 protons plus 8 neutrons. The most basic isotopes are hydrogen isotopes, hydrogen being the most basic element. So we have hydrogen 1, hydrogen 2, and hydrogen 3. So hydrogen 1, it has a nickname. It's sometimes referred to as protium, and it's just got 1 proton. So you think 1 proton plus 0 neutrons gives it that mass of 1. But if we add a neutron, now we have a mass of 2. So it's called hydrogen 2, and its nickname is deuterium. And then if we add 1 more neutron, we have hydrogen 3. Its nickname is tritium. So all of these are isotopes of hydrogen. Let's now talk about how many electrons are in an atom. So we've been talking about the nucleus with how many protons and neutrons, but then remember there are the electrons that are way beyond the nucleus that are swarming around going very, very fast. We sometimes say they are smeared out around the nucleus at a relatively large distance. Now, every particle has an electrical charge. Each proton has an electrical charge of +1. Each electron has an electrical charge of -1, so they are equal and opposite to each other. If you put a proton and electron next to each other, they will actually balance each other out, and you can just add the numbers. The +1 plus the -1 will cancel out, and it gives a charge of 0. Usually atoms are electrically neutral. Neutral means having 0 charge. And what this means in terms of the particles is that usually there are equal numbers of protons and electrons. Not always, but nature prefers there to be equal numbers of protons and electrons. Now, for example, carbon has 6 protons, always, by definition. So if it's neutral, it also has 6 electrons. And you can do the math. Every proton is a +1, so +1, +1, +1, +1, +1, +1. And then if it has 6 electrons, minus 1, minus 1, minus 1, minus 1, minus 1, minus 1, and it all comes out to be 0 charge, making it neutral. When we talk about electric charge, by the way, neutrons don't come into the conversation because neutrons are neutral. They have 0 charge. A minute ago, I said that atoms usually have equal numbers of protons and electrons, but it is possible to take away an electron or even to add electrons. For purposes of this class, we'll mostly be dealing with taking away of electrons. If an electron is taken away, the atom becomes an ion, and we say that it's been ionized. So if you insert enough energy or the right amount of energy into the atom, it can just strip the electron away. And remember back to the previous video, it was chapter 5, part 2, where I talked about ionizing radiation. And remember, that is gamma, X-ray, and ultraviolet. Those are electromagnetic waves that have enough energy to strip the electron away. So think about the carbon atom that when it's neutral has 6 electrons to match the 6 protons, but if you take one away, now you only have 5 electrons. So carbon that has been singly ionized, that means one ionization has taken place, 1 electron's been taken away. It now has 5 electrons, and it has a charge of +1 because the 6 pluses of the protons and the 5 negatives of the electrons add up to +1. So this is what the upper right hand of the chemical symbol is used for. Sometimes it'll be written as a plus sign. Sometimes it'll be written as a +1 or 1 plus. But that means it's been singly ionized. It has a charge of +1. Now, if we take away another electron, then it's been doubly ionized. So a carbon atom that's been doubly ionized has had 2 electrons taken away, so it only has 4 electrons now. It can be written like this, either C++ or C2+, and that means it has a charge of +2. So if you see the symbol C2+ or C++, you think it has a charge of +2, meaning from its neutral state, it had 2 electrons pulled away from it. So if you want to know how many electrons are in there, you have to think, what was it in its neutral state? Well, if it's carbon with 6 protons, it originally had 6 electrons. And if 2 have been taken away, now it only has 4. Let's look at this chemical symbol here. So I've shown you the upper left hand, lower left hand, and upper right hand. Remember that, let's start down here at the lower left hand. This number, which doesn't always have to be there, is the atomic number. So that's for magnesium, which is what we're looking at here, that's 12. The mass number is the protons plus neutrons. In this case, we're thinking about an atom that has 12 protons and 12 neutrons, so a total of 24. Over on the right-hand side, upper right, is the charge. Now, in this case, we're looking at something that has had 2 ionizations, so it has a charge of +2. And so what's leading to that charge of +2 is the 12 protons, and then it's got 10 electrons. So the 12 positives plus the 10 negatives gives us a charge of +2. And of course, the chemical symbol, each element has a symbol that's either 1 or 2 letters. In this case, magnesium is Mg. So let's think through some of these. A neutral carbon-14 atom has how many protons, how many neutrons, and how many electrons? So when approaching this question, think about the atom, the element itself, and how many protons it has. So usually it's best to think of protons first. If it's carbon, and you can look it up on a periodic table, there's one in the back of the book. You can Google search, find a periodic table. But carbon is element number 6. As you go through the periodic table from left to right, zigging back and forth, you have hydrogen, helium, lithium, beryllium is 4, boron is 5, and carbon is 6. And that tells us how many protons there are. So there are 6 protons because it's carbon. Now let's think about the number of neutrons. And that mass number 14 is going to give us the clue. So if there are 6 protons, and there are a total of 14 particles in the nucleus, you do the subtraction and think how many neutrons there are. Well, 14 minus 6 gives 8 neutrons. And then you can see the 6 protons plus the 8 neutrons, they should add up to give that mass number 14. Now, the last question, how many electrons does it have? And the key word is right here, that it's neutral. If it's neutral, electrically neutral, that means that there's as many protons as there are electrons. And as I said before, this is the normal state that atoms tend to occur in nature. So having 6 protons and being neutral, it has 6 electrons. Let's do another one. Neutral helium-3 has how many protons, neutrons, and electrons? And the first thing you should do is think about how many protons. So if it's helium, and this is one, there's only 2 elements I told you need to memorize. The others you can look up on a periodic table as needed. But helium, I want you to remember, is element number 2. That's its atomic number. That's the number of protons. And so, how many neutrons does it have? If we're talking about helium-3, helium with a mass of 3, how many neutrons does it have? 1 neutron, because it's the 2 protons plus the 1 neutron that make up that mass of 3. And finally, how many electrons? And you should go back to the description that talks about, is it neutral? Is it ionized? How much is it ionized? In this case, it's neutral, which means it has equal numbers of protons as electrons. So 2 electrons. So there's a model of it right there. 2 protons, 1 neutron in the middle, and then the 2 electrons. Let's do this one. A certain atom has 3 protons, 4 neutrons, and 2 electrons. Identify it. And so when I say identify it, that means what element is it? What's its mass? So we can identify the isotope. And let's talk about its charge as well. So we're going to focus on that number of protons again to tell us what element it is. And element number 3 is lithium. And now let's think about what isotope of lithium it is. So what is its mass? 3 protons plus 4 neutrons gives an atomic mass number of 7. So we're dealing with the isotope of lithium-7. And finally, we need to think about its charge. Lithium has 3 protons. This particular atom that we're considering only has 2 electrons. So you should think, if it were neutral, it would have 3 electrons, matching the number of protons. But it doesn't. It only has 2 electrons. That tells us that 1 electron has been stripped away. So we can say that it's singly ionized. We can also say it has a charge of +1. So the answer is we have singly ionized lithium-7. And there's the symbol. We've got on the lower left hand, we have the atomic number 3. On the upper left hand, we have the atomic mass number of 7. And on the upper right hand, we have the charge of +1. So when it comes quiz time and test time, you should be able to do these types of questions that you've been seeing in this video. Okay, here's a symbol. How many protons, how many neutrons, how many electrons? And so it is boron, and we go to the lower left hand to find the atomic number that boron always has, 5, and that tells us how many protons there are. Now we want to know how many neutrons. So we go to the upper left hand, and we see it has a mass of 8, and that's the total number of protons and neutrons. Well, out of that 8, we already have 5 protons, so 8 minus 5 gives us 3 neutrons. And finally, how many electrons? You see that charge of +3, and you can think that means that 3 electrons have been stripped away from its neutral state. But what was its neutral state? Well, if it's neutral, it has 5 protons, but 3 have been taken away. So it has 2 electrons. So 5 protons means neutrally it had 5 electrons, but 3 have been taken away, so 2 electrons. And we identify this as triply ionized boron 8. There's a picture of it right there. Now that you've learned about what atoms are made of, I want to talk about electric charge, which I introduced earlier in this video, and give you some of the foundation for what holds atoms together. So as I've mentioned before, these different particles have different electric charges. A proton has a charge of +1, a neutron has a charge of 0, and an electron has a charge of -1. What this means is that protons and electrons have charges that are equal magnitude, but they are opposite, so positive and negative. Neutrons are neutral, meaning they have 0 charge. So we think about this helium-3 atom. It's got 2 protons. The red circles are the protons with the plus signs in them. The purple is the neutron with 0 charge, and the little blue circles with the negative signs are electrons. And so this atom, if we count up the charges, we have 2 positives and 2 negatives, and so it's a neutral atom. An important concept when understanding electric charge and how electric charges work together is this. Opposite charges attract each other, and like charges repel each other. So when I say opposite, I mean positive and negative. Like charges would be 2 positives or 2 negatives. And so as we look at this helium-3 atom in the diagram, the 2 protons actually repel each other. The electrons are attracted to the protons because electrons are negative, protons are positive, and that's actually what keeps electrons in orbit around the nucleus, because they are attracted to the nucleus. So there's the phrase that I want you to remember down at the bottom. Opposite charges attract each other, like charges repel each other. And so if we have 2 protons, each of them being positive charges, they will repel each other. Now, in this diagram, it doesn't so much matter that they have charges of 1. What matters really is that they are positive, so they will repel each other. Although the greater those charges, the more the repulsion is going to be. But for right now, it's just important to understand that the positive and the positive will repel each other. And you can see in the diagram, these green arrows represent the forces. They are forced away from each other. 2 electrons will do the same thing. They're both negative. They are both like charges, so they repel each other. And by the way, this is also a good example of Newton's third law, which says that if you have particle A acting on particle B, there will be an equal and opposite force of B acting on A. And so the electron on the left is pushing the one on the right farther to the right, and the one on the right is pushing the one on the left farther to the left. So there's those green arrows represent the equal and opposite forces. Like charges repel each other, but opposite charges attract each other. So here we have a proton and an electron, and they are attractive to each other. It's much like gravity, the attraction between 2 masses. So they are pulling towards each other. The proton on the left is being pulled towards the electron. The electron on the right is being pulled to the left towards the proton. Now, neutrons do not have any electrical charge, or they have 0 electrical charge, so there is nothing attractive or repulsive about them. So when we talk about electrical interactions, neutrons don't even come into the conversation. So here we have a neutron and a proton. They are not opposite. They are not like charges, so there is no force between them. Same with a neutron on the left and an electron on the right. They are neither opposite charges nor like charges. So a neutron never feels any electrical attraction or repulsion. Let's consider now a doubly ionized helium-3 atom. Doubly ionized means it's had its electrons, 2 electrons stripped away. And so it's got 2 protons, which means in its normal neutral state, it should have 2 electrons, but it's been doubly ionized. So 2 electrons have been stripped away. So there's the symbol for it where, remember, helium is atomic number of 2 down there to the left. It has an atomic mass of 3, so up to the left. And since it's been doubly ionized, it's had those 2 electrons stripped away from it, then it has a charge of +2. And you can look over the picture and you count. There's +1, there's another +1, that's +2. Of course, the neutron is 0, so it has a charge of +2. Now, I've said before that nature prefers atoms to be neutral. Usually in nature, atoms are neutral. That's not the case in this picture right here, but I want to get into why atoms are usually neutral. So here we have an ion with a charge of +2. And somewhere in the vicinity, there's most likely going to be a stray electron somewhere, and the electron is negative. And it is attractive then to this doubly ionized helium-3. So being attractive, it will tend to go towards it. It'll be pulled towards it, and it will eventually join the helium-3 nucleus. And so it's joined. And now let's look at this. Now we have a singly ionized helium-3. Singly ionized because it should have 2 electrons, but it only has 1. So it's as if 1 has been stripped away. Now notice this helium-3 atom, it's got a vacancy right here. It's waiting for an electron to come along. Now, since it has a charge of +1, it's attractive to another stray electron that you can see down there to the right, which has a negative charge. And so if there happens to be a stray electron in the vicinity, and there probably will be, it will join to that helium-3 nucleus. And so there it is. So now it is a neutral helium-3 atom. Now, if there's another stray electron in the vicinity, that stray electron is not going to be attracted to this atom because this atom is neutral. It has 0 charge, just like a neutron has 0 charge. So it's not going to attract any more electrons to it. Let's talk about electrical repulsion inside the nucleus. Remember the phrase opposite charges attract each other, like charges repel each other. So the question is, what keeps the nucleus from flying apart? And the reason I ask that is because think of what's inside the nucleus. Protons and neutrons. Neutrons don't feel anything electrically, but think about those protons. Inside the nucleus, you have many positively charged particles, known as protons, all bunched together. But like charges repel each other. Those protons should all be flying apart. The nucleus of every atom should be flying apart. If there were only electrical forces going on, there would just be that electrical repulsion. So what keeps the nucleus from flying apart? It is a stronger force than the electrical repulsion between the protons, and it's called the strong nuclear force. The strong nuclear force is a force that acts between protons and protons, between protons and neutrons, and between neutrons and neutrons. So between all the different types of particles, pairs of particles that can be in the nucleus, the strong force holds it all together, and it overwhelms the the repulsion between the protons. And that is the end of part 4 of chapter 5. Have a great day.